Now, when we deal with problems on gas laws, analysis of graphs, especially the PV graphs, VT graphs, and various different kinds of graphs which involve the thermodynamic parameters, analysis of these graphs becomes really important. So, here are some problems based on analysis of gas laws and the graphs specifically. So, here we have a graph which is P versus V, and then this graph corresponds to temperature T2, this graph corresponds to temperature T1. Now these were done, the analysis or the plotting was done for same mass. So in both the situations, the mass was kept same. So let's go to the question now. The question is, which is higher? Is T2 greater than T1 or T1 greater than T2? Which is true? How do we find this? So the only equation that we have is PV equals to nRT, and here from this graph we can say that temperature is what we are talking about. So that is PV by nR. Now this quantity was kept constant because it was for the same gas and the same mass. So temperature is directly proportional to PV is what we get from here. Now clearly from this graph you can see that this PV value is less compared to this PV value. So definitely PV value for T2 is greater as seen from the graph, and hence we can say that T2 is greater than T1. Here we have another problem. So again it's a rectangular hyperbola wherein the P versus V graph is drawn, and that is at constant temperature. So this is a problem pertaining to isothermal process or Boyle's law. So for two different masses, they plotted the graphs and they plotted at same temperatures. We have to compare M1 and M2. Again, let's get back to the ideal gas equation. And here we have PV equals to small mass m by m RT. So this is the reference point for us now. So this is the subject of the formula. Let's make it the main reference, and this goes, and what we get is this m by RT. You can clearly see that this is a constant, and hence mass is directly proportional to PV. So it's the same kind of logic that we had in the last problem, and so we can say that since this is having a higher PV value than this, we can say that M2 is greater than M1. Here we have another equation, here we have another graph, and this is not a usual graph that we have seen till now. So you can see that it's a PT graph, and the graph that we had basically seen for volume constant, it was this. Now we have this kind of a graph wherein the pressure is varying according to the temperature, and this is for a given mass. So we have to draw conclusions on delta V, that is whether the volume is increasing, decreasing or constant. You can clearly see that this is not the same graph as we had seen earlier. So if the volume is constant, then it's a graph which is passing through origin, which is like this. But now it is not passing through origin and it is starting at a certain point. So which means that it is not pertaining to constant volume. Now to find whether the volume is increasing or decreasing, we'll have to actually analyze the equation. So any graph which is of the form, this is y, this is x, and if it is something like this, wherein this quantity is, you can say A, then we can say that y is equal to some slope plus A, or for that matter, it's C, which is famous. Y is equal to mx plus C is the graph. Similarly, we can say that here the graph can be of the form P is equal to A times T plus B, where B is a constant and A is the slope of that graph. Now, what is the slope of this graph? Can be. So, why I have chosen this is because when we go to PV equals to nRT, this is a constant, this is a constant, and we can say that volume is nR T by P. This is the relation that we have. So volume is directly proportional to this quantity T by P, and this is what we have to analyze. So if this quantity is increasing with time, then we can say that the volume is increasing over this length. That is, along with the rise in temperature, the volume is increasing. That is what we can say. But now we have to analyze this part. So let's divide this throughout by temperature. So if I divide throughout by temperature, I'll get something like this. P by T is equal to A plus B by T. Now you can clearly see that the temperature is rising. So if the temperature is rising, and if I define, let's say this is at one combination, that is at A, PA by TA is A plus B by TA, and PB by TB, we can write A plus B by TB. So definitely we can say that this quantity will be more than this quantity, because certainly here the temperature will be higher. Now because the temperature is higher at this point B, we can say that B by TA is more than B by TB, because simply because here the denominator is low, here the denominator is high. So this quantity overall will be lesser than this. And so A being a constant, PA by TA, this will be higher than PB by TB. So we get a relation like PA by TA is higher than PB by TB. But this is not what we are looking out for. What we are looking out for is temperature by pressure, because this is our reference equation. So we can say that TA by PA is less than TB by PB. Now this is done in accordance with the rules that we have learnt in inequalities, and this gives us a clear idea that this ratio is more at B compared to what it is at A. Hence we can say that volume at B is greater than volume at A. So the volume is increasing along with the temperature. So now we have a problem which states that there is a gas at 27 degrees centigrade initially, and from 27 at constant temperature there is a pressure rise. So earlier at this point it was 100 Newton per meter square, and this rises to 150 Newton per meter square. We have to calculate the change in volume. Now if temperature is constant, we are going to use the Boyle's law, and if you are using the Boyle's law, we will have P1 V1 equals to P2 V2. So the volume initially is 4 liters, pressure is 100, pressure 2 over here is given as 150, and this is the volume. So we can find as volume 2, that is 25 4s are, and then 25 into 6. So this comes as 2 by 3 into 4, which is V2, and this comes as 8 by 3 liters. Now if you find the change in volume, it is V2 minus V1, which is 8 by 3 minus 4, which is minus 4 by 3 minus 1.33 liters. That is the change in volume. So volume has decreased. That's what it means. The negative sign only tells us that the quantity has decreased. In second case, it is then heated at constant volume. So here we are going to use the equation P1 by T1 equals to P2 by T2. Now here the pressure as calculated earlier at constant pressure, and temperature is varied. So earlier the temperature is 27, and now from 27 it is rising to 127. Earlier the volume is given as 4 liters. Here we have to calculate. So 27, 4 by 27 plus 273, because what we have to write is in Kelvin. And this also will be x by 127 plus 273. So calculating it further, we will get the answer. So the equation that we have now is P1 by T1 is P2 by T2. Let me just rewrite it over here. 4 by 27 plus 273 comes to 300 Kelvin, and this would be x by 400. So overall what we get is 16 by 3 is what we get. So x, oh, this is at constant volume. So pressure 1 was at 100. I'm really sorry. This is 100 and this is going to be so here the temperature 1 that we have is 300 and the pressure 2 is what we have to calculate. Now here the pressure that we have to actually take is 150 because we have already reached this stage wherein the pressure is increased from 100 to 150. So we are in a situation wherein already the pressure is 150 and it is then heated at constant volume. So we will take the pressure as 150 and then we have to calculate P2. So this will come out as 150 by 300 into 400, which is 200 Newton per meter square. That is the answer of this question. Let's take up the next problem. So it says that there is a balloon partially filled with helium and it has a volume of 30 meter cube at Earth's surface. So this is the condition 1 for the volume, which is 30 meter cube given to you, and the pressure in this particular condition is 76 centimeters of mercury. So let's write it as it is. The temperature at this point is 27 degrees centigrade, and so the temperature can be taken as 300 Kelvin because 27 degrees centigrade is 300 Kelvin. Now balloon rises to a particular height, and in this condition the pressure and temperature conditions are given to us. So pressure is given as 7.6 centimeters of mercury and the temperature is given as minus 54 degrees centigrade. So it's going to be 273 minus 54, which comes out as 219 Kelvin. Now all these things are given to us. What we have to find is the increase in volume. So let's make use of all the data that we have just found, and we are going to use the equation PV equals to nRT. Now if I make use of all this data, we see that pressure, volume and temperature all are varying at one point and nR is the only constant. So we can say that PV by T is a constant. We can use this equation in this particular problem, and we can say that P1 V1 by T1 is P2 V2 by T2. So P1 is 76 given to us, volume is given to us earlier as 30, temperature T1 is, this is T2, temperature T1 is 300, pressure P2 is given as 7.6, volume is unknown X, and the temperature T2 is given as 219. Now we can clearly subtract all of this, divide 7.6 ones are, this is 10s are. So 30 into 10 is 300 and this 300 and this 300 will go. And ultimately what we get is X is 219. So it is 219 meter cube of the volume at that particular height. So the change of volume, what we want, or the rise in volume will be V2 minus V1, which is 219 minus 30, which is 189 meter cube. That is the answer of this question.